Hello.
Hello, I can hear you.
Sorry?
I say hello, I can hear you.
Oh, okay, that's great.
Okay.
Здравствуйте, Григорий.
Здравствуйте.
Ага, хорошо. Сейчас, видите, пока еще только начинают люди подходить, но уже пришел китайский студент, судя по всему.
Мгм.
Вот это.
Да,
Я вас, прошу прощения, когда я первый раз рассылал, я забыл сменить имя предыдущего докладчика.
да ничего страшного.
Мгм.
Я тут в двух экземплярах, но это для страховки.
Да, я понимаю. Я правильно указал вашу аффилиацию как университет Хайфа? Сейчас,
Да.
да,
Мгм.
хорошо. Окей. Подождем немножко еще. Сейчас народ подтянется. Мы обычно начинаем, значит, в независимом университете в 6 или в 6:30, но там всегда с небольшим опозданием, потому что когда это начинается в оффлайне, то время тратится на то, чтобы подключить оборудование и так далее. Народ привык и, наверное, не торопится подключаться.
Ну, это так ожидаемо.
Я еще успел написать, когда вам писал, я еще, не знаю вашего адреса, сначала написал Борису Львовичу, но он не ответил. Я думаю, что он слишком занят.
Он, он иногда не читает почту,
Ну, я тоже так понимаю, да.
иногда подолгу.
Ничего страшного. В общем, я хорошо, что Даниил смог с вами связаться, у него был какой-то контакт.
М.
Так, пока 3 слушателя, вы и я. Давайте еще подождем немножко.
Еще полминуты по моим часам.
Ой, на самом деле, думаю, 5 минут нужно ждать будет как минимум. Я сейчас напишу руководителю нашего семинара,
Мгм.
чтобы он тоже присоединился. Так, которое сейчас у вас там сейчас? У вас московское время совпадает?
Московская, да, 5 часов.
Понятно, отлично. Мгм.
А вы в Китае, да?
Да, да, тут сейчас 10 часов вечера.
Мгм.
Так вот. Тут довольно много, я сказал бы, сейчас собирается народу и из России, и из других стран, по-видимому, по крайней мере, постдоков я видел много иностранных.
Позиций много у них, это я видел.
Вот, так что в случае чего приезжайте тоже.
Иметь в виду. Спасибо.
Так, кто-то еще к нам присоединился. Угу. Я, Антон. О, интересно, Антон Савин к нам присоединился. А это, я не знаю, 899-4326.
По-моему, это
Извините, это кто?
это номер этой самой конференции.
Да.
Находится.
Можно опросить человека. Будьте
Я
добры.
думаю, это я просто неправильно написал.
Вы это, извините, я... это
Я
вы?
Баранд Арачальян.
Варант, здравствуйте, Варант. Все, это вы.
Здравствуйте.
Здравствуйте.
Видите? Хорошо. Отлично. Ну, слушайте, у нас прямо сегодня много народу, причем много людей иностранных. Джунху, странно, что не пришел, как раз мой студент не пришел, которому я просил прийти. Вот, Дзирань такой, Ван Дзирань, которого я как раз просил прочитать вашу диссертацию, вот, и задавать вопросы. Но он что-то не пришел пока.
Я ее собираюсь переписать, потому что текст там такой, что на архив пока класть нельзя.
Ну, это не является недостатком с точки зрения, так сказать, науки, с точки зрения того, что там содержание, а презентацию можно полировать до бесконечности. Это вот по моему я опыту знаю. Вот. Так, давайте еще 2 минуты подождем. Почему-то не подключается Саша Жиглов. Он сейчас скоро подойдет. Это соруководитель семинара Александр Жиглов с нашей кафедры тоже. Угу. Так, значит, насчет следующего раза я тогда сразу давайте всем присутствующим скажу, что у меня есть предполагаемые докладчики. Не знаю, кто конкретно, там в конечном итоге будет, но пригласили 2 людей. И кто из них в итоге сможет выступить, непонятно, но один из них точно будет. И на 3 октября у нас уже тоже есть докладчик. Что касается дальше, тогда, если у кого-то есть желание выступить самостоятельно, или вы знаете, кого можно пригласить, уже там в октябре говорите. У нас начиная где-то с 3 октября в основном места свободные, вакантные. Так что милости просим. Так. Вот пришел Саша. Okay, I think it is good time to start our lecture, our today's seminar. And the speaker today is Grigoriy Papayanov from the University of Haifa. And he is going to speak about deformation, quantization, and formal geometry, if I'm not making any mistake.
Yes.
Okay. Now I can share your screen and we'll go on.
Yeah. Can you see the presentation?
Yeah, we can see everything.
Okay, that's great. So, I mean, first of all, thank you very much for the invitation. And second, I want to apologize in advance because I'm not in a very formal environment and the street might be a little bit loud. So if something like a garbage truck happens outside of my windows, I apologize for that. So yes, I would like to tell about not like a solution to a deformation quantization problem, but more like an explanation of a method of solving the deformation quantization problem as done by Fedosov and by Nastzigan and by колледием без рукавников in different settings by applying a little bit of homotopically algebraic, more precisely L-infinity theoretical flair to it. So, and let me start by explaining what one part of the title of my talk is, and it's the formal geometry. And the formal geometry is a method of studying manifolds and geometric structures on them by means of studying them in a formal neighborhood of all points. And the most important definition in this direction is the definition of a jet of a manifold. So there is a natural bundle with over any manifold with fibers being power series algebras, which controls a lot of the geometry of this manifold. So let X be a manifold, and it could be a smooth manifold, it could be complex analytic manifold. I mean, if I want to talk about transition functions, I don't want it to be algebraic, but I mean, it could be a smooth algebraic variety maybe later in the process of the talk. So let X be a manifold with some atlas and some transition functions. And we can take the Taylor series of these transition functions at every point, and we'll obtain one cycle with values in the group of the automorphisms of formal disk, or in other words, automorphisms of this power series algebra of several variables, the number of variables being the dimension of the manifold. So if it is one cycle with values in this group, it defines a principal bundle under this group. And we call this the formal coordinate system bundle of X. And we have this notation with X coord.
Sorry, do you consider complex varieties?
I mean, if I put, can you see my mouse pointer?
Yes, yes.
Okay, if I put here C, I consider complex varieties here, but if they're real, there could be R.
Okay. So you consider just in usual differential geometric sense, right?
Yeah. So just smooth complex manifold.
Okay.
I mean, yeah, every time I want to define a base field, I want to put in the base field annotation, it will be C, but it's applicable in a more wide variety of situations. Yes, and we have a principal bundle over this group of automorphisms of this formal power series algebra, and we have a module over this group because this group of automorphisms act on the algebra itself. So we can write down the associated algebra bundle, this fiber product, and it is called the jet bundle. It's a bundle of algebras over X. And the fiber of the jet bundle at a point X, it could be thought of as algebra of functions on a formal neighborhood of this point.
Yes.
And consequently, the fiber of formal coordinate systems bundle X coord at a point X is a space of isomorphism between these functions on the formal neighborhood of a point and just functions on a formal disk. Or alternatively,
This jet bundle is just the standard infinite jet bundle, which we study.
yes. This is a standard infinite jet bundle.
Just another point of view on it.
Yes.
Sorry, but you use notations from algebraic geometry and then formal spectrum. At the same time, you consider just differential geometric manifolds. A little bit confusing.
Yes, I mean, if you this let's say I'm in a setting of something like complex spaces.
Okay.
Complex analytic space. There is a definition of a complex space which is similar to the definition of a scheme.
Yeah, I see. But before you told about real analytic case, so it was so you will consider mostly complex analytic spaces, right?
Mostly complex, yes.
Okay.
I mean, if I want to talk about formal disk as something geometrical, so I'm forced to consider like formal spectrum, but I mean, formal spectrum of this algebra A is just something of which this algebra is the algebra of functions of.
Yes, yes, I understand. Just I'm confused about notations, because if you use formal spectrum, then necessarily, usually people think about standard Noetherian rings from algebraic geometry, defined over algebraic
I
closed
mean,
field.
I want to stay in the realm of
So-
complex geometry, and
Okay.
I mean, if I have a complex manifold, I can take completion of the algebra of functions at a point.
Yeah, for complex, it's okay. I mean, if you consider real varieties,
Even for the real
then
varieties, I mean, I have a O, which is an algebra of functions. You can think this is an algebra of smooth functions. And if I have a point, I have an ideal of a point in this algebra of
Yeah.
functions there. And I can take this completion, and it will be the formal power series algebra. Even if I start from a smooth real manifold.
I mean, well, for non-analytic functions, the rings could be not Noetherian. I mean, if you consider
It could be, I don't care. I can take this. I have a ring, I have an ideal, I have completion.
Mhm.
The result of this completion is always the formal power series algebra.
Mhm. I mean, just if you consider, well, there are many subtle questions. Because if you consider completion, then since the ring could be not Noetherian, then the intersection of ideals could be not zero, so it could be not separated. So, well, okay. Let's
I
assume
mean,
for
yes,
simplicity.
yes, yes. In a smooth case, the intersection of all these ideals is not zero,
Yeah.
but it doesn't
Okay.
prevent
Any
me
case,
from
I mean,
taking this abstraction.
you consider here only something like formal power series, right?
Yes, yes.
Must,
I mean, if I take this completion, I lose every information related to
yes.
non-analytic function. I
Okay.
I start to see only Taylor series.
Okay.
So actually, I mean, in smooth case, there is a different way to construct the same jet bundle by considering limits of finite jet bundles, which are just usual bundles in the usual sense.
Yes,
So
yes.
I think it is just splitting a hair here. In smooth case, there is an alternative way to formulate this, and we can always, when we speak about smooth case, we can always just pass to that formalism. Just go to the use that formalism. Okay.
Yes. Also, again, there is a subtle question, because if you take, say, a non-analytic function like this famous function of smooth of non-analytic function, then it cannot be determined by its Taylor series in a point, and then by this completion you will lose it. You will lose functions.
Yeah. I mean, I lose some information. Yes.
So therefore, we speak about jets of functions, and it is known that for every it is known, I think it's Borel theorem, that for every formal power series there exists a unique jet with this corresponds to this formal power series. So yeah, I think it's okay. Yeah.
I mean, yeah, I definitely lose some information if I work with non-analytic functions, but I mean, still, I can take this.
Yeah, I understand. I just want to specify. Also, it's useful for students because this question are subtle. Yeah.
So I mean, yes. So I would be very glad if you will ask me questions. I have 40 slides in my presentation.
Okay.
I don't know whether it will be too short or too long, so I think we'll figure it out. But yes.
Well, it depends. Yeah. Okay.
Yeah, but just so there is an estimate on the board. I have 40 pages. So okay. And if I have a jet bundle, and if I have a function regular, then I can take the jet of this function, which in local coordinate, I just at every point I just take a Taylor decomposition of this function. with respect to the coordinate system that, well, I have, that is given to me by an atlas. So there is one question that we may ask ourselves. So suppose we have a general section of jets, of jet bundle. So it is just a formal power series which smoothly depend on a point of our manifold, and just locally, they are on a disk. So when does there exist a function such that our function with respect to formal with values in formal power series is a jet of this function? And the answer to this question is well known. The only condition that we need is that we need the partial derivatives to commute. So, of course, if we have this function, and if this function is jet of something, that this something may only be this f0, this free term that freely varies with the point. And if we have some functions that we want to think as partial derivatives of this function f0, and the only thing that we need is that if you take like f1 and we take d over dx2, we will have something that f12 here.
There will be no problem with convergence, right? Do you mean?
I mean, we already have an actual function. f0 is a free term of our formal power series functions. It's already an actual function.
Oh, I see. So just yeah.
So we take jet of it and we want to compare two jets that already exist.
Yeah, I see. Thanks.
Mm-hmm. And so if one wants to write down this condition of the commutation of partial derivatives in a formulaic way, one can write this operator. So you can sorry, I have x here and z here, but x and z are the same things. Sorry about that. And t is a formal variable. And we have this operator, which is d, the RAM differential minus this sum over the basis. And if our jet is our jet vanishes under the application of this operator, then our jet is a jet of a function f0. And so what is this operator? This operator is a flat connection. It's a flat connection that is actually globally defined on the jet bundle. One can check this. And it is called the Grothendieck connection. And the space of flat sections of this Grothendieck connection is a space of globally defined functions. Okay, so and now we want to talk about bundles with connections, but when we talk about, for example, vector bundles, we can talk about them in two ways. We can talk about vector bundles per se, or we can talk about the associated frame bundles. And the point of view from frame bundles is the equivalent, but a frame bundle is a little bit of a richer structure, because how do you obtain a vector bundle from a frame bundle? You take a representation of a structure group, JLN in this case, and you take the fiber product. So you can take different representations, so you can obtain a lot of vector bundles from the same frame bundle. So this point of view is a little bit richer. And connections, we can talk about connections in both of these languages. So if you have a vector bundle, you can think of a connection as a differential operator with certain properties. Yeah, differential operator that locally looks like the RAM derivative plus a, where a is g valued one form. And we can talk about connections on a frame bundle is a form on a total space of a frame bundle. It's also g valued, but it's a form with certain properties, such that it restricts to each fiber by a canonical g valued form on the Lie group itself.
What is Russian for solder form? I have never seen this terminology in Russian? Actually, they only
I
speak
have no idea. And
in Russian. They only speak about connection on principal bundles and connection form on principal bundles.
yeah, I don't know the short name for this in Russian, but soldier по-русски это припой.
Yeah, I understand. Yeah,
Mhm.
this.
Because I don't. I have no idea why the name is like that. But also
But yeah.
I think the name is a little bit outdated. I'm not sure if it's used in modern literature anymore.
Okay, thanks.
May I ask also some bibliography question? Yeah, but the name of Grothendieck's connection. Am I, as far as I understood, this terminology comes from Grothendieck's work, right? So I mean, probably it was written in SGA somewhere, right?
EJ4. I think EJ4 is a good.
Mhm.
Source of,
Mhm.
like when they worked out the
SGA4, okay.
infinitesimal
Yeah.
site and all this. Yeah, it's EJ4, I think written by the lead, but
And there he considered also which kind of varieties he considered there, just complex analytic or
no,
any.
they work in the algebraic setting.
Okay.
Let's see, again, not everyone calls it the Grothendieck connection. Sometimes it's called like the canonical flat connection on the jet bundle, but I think this is the shortest name, so I'm using it. Again, so we have two ways of thinking about connections on a vector bundle, and we have a Grothendieck connection as a differential operator. But if we want to write down its solder form, then we will encounter a problem, and the problem is this derivation of the formal power series d over dt. It does not integrate to any automorphism of a formal power series algebra. Yes, so if you have a disk and the vector field d over dt, it does not generate a flow on the disk because the disk is only locally, and informally locally you don't even have place to localize. So we are forced to work with the so-called Harish-Chandra pairs. So a definition: a Harish-Chandra pair is a Lie algebra L, a Lie group G, and the Lie algebra embedding from the Lie algebra of G to L, such that the corresponding representation of G on L, like the adjoint representation here to here, integrates the representation of G. So again, we need some generalization because we are working with algebras and groups that are not Lie, because the group of automorphisms of a power series algebra is infinite dimensional, but it's a projective limit of finite dimensional Lie groups. So and there is a good theory of Lie theory for projective limits of finite dimensional Lie groups. You can take projective limit of the corresponding Lie algebras, and this association works more or less as expected. So what doesn't work is that you cannot associate a group to a Lie algebra, and this is a good example. So you have a group of automorphisms of a formal power series algebra, and its Lie algebra is a group of vector fields on a formal disk that vanish at zero, because all automorphisms of formal power series algebra, they preserve the maximal ideal. So they fix a point.
You mean continuous automorphisms, right?
I think they're all automatically continuous, because maximal ideal is preserved, so the MAD topology is preserved. So they're all automatically continuous.
Well, I mean you consider only automorphisms of local algebras then, we have.
I mean, I have
Yes, yeah.
algebra A. It is local. Algebra.
Yes,
No.
yes. I mean, I'm afraid that if you can consider arbitrary automorphisms, that could be not continuous automorphisms in general.
No, I think
Some problem.
if you consider the formal power series algebra with adic topology generated by a maximal ideal.
Yeah,
then-
but it's topological algebra. That's why I'm asking to consider continuous automorphisms or not, because you can take some infinite transcendental basis considered just like a
Yeah, I think this doesn't
extension, and then you can construct arbitrary automorphisms which cannot be continuous a priori, not. But if they are continuous, then of course they need to preserve
No,
maximum.
I think they all automatically will be continuous. At least if I have a finite number of generators, then I cannot do anything like that.
No, because the ring of power series is not has infinite transcendental basis, even for one variable. So it's necessary to say what continuity of automorphism.
I mean, I'm afraid I don't understand what transcendental basis is, because I'm not talking about automorphism of a field of Lorentz series.
No, but it's a commutative algebra, right?
Yes.
Then, and since it's just a formal power series, it's commutative algebra. Well, it's commutative ring of finite crude dimension, but from the point of view of commutative algebra, the transcendental degree of it is infinity. And that's why if you consider just arbitrary automorphisms of such an algebra, they could be not continuous in general. But if you consider only automorphism for topological algebra, then of course they will preserve maximal ID.
I mean, I'm willing to make this restriction, but I think all of them are continuous automatically. So maybe we can.
No.
We're talking about automorphisms which are limit of some automorphisms of finite elements, and
Yes, that was my question. If you consider automorphism preserving some structure as a topology, or
I believe it was said, Grisha said that he considered the group which is also profinite limit of the groups of
yeah. Then it is an automorphisms in this category of profinite groups. And that's
everything is a category of profinite, and
Okay.
it's automatically continuous. I think it's
yes.
not fair.
Still,
Okay.
I think it's topology is generated by maximal ideal, and the maximal ideal is preserved by any automorphism because it's unique.
Continuous. In that topology, right? Okay, but it's just a remark.
Okay, yeah. So anyway, yes. So it's you can just think that yeah, if yes, a group of continuous automorphisms. Okay, and its Lie algebra is a Lie algebra of derivations of this algebra that preserves the maximal ideal. But not all derivations preserve the maximal ideal. For example, derivation d over dt does not. It's a vector field on a formal disk that does not vanish at a point. So this is an example of a Harish-Chandra pair. And of course, if I have a genuine Lie algebra and I have a genuine Lie group and a closed subgroup in it, then I have a Harish-Chandra pair like this, of small group and big algebra. And also I can take here only the linear group inside the group of all automorphisms of formal disk. And this is also an example of Harish-Chandra pairs that we will be using. And another couple of examples come from symplectic geometry. So if we consider a formal disk that has a symplectic structure on it, formal symplectic form, and by a formal Darboux theorem, it doesn't matter which symplectic form we take because they're all equivalent to each other by change of coordinates, formal coordinates. We can take the group formal symplectomorphisms of a formal disk, and we can take a real. Sorry? yes, the group of formal simply ectomorphisms of a formal disk, and you can take the Lie algebra of Hamiltonian vector fields. So we have also two examples of Harishchandra pairs. One is similar to the coordinate Harishchandra pair that we used before, and the other one is also with a group part reduced to a linear part. And we have a group. Over a group, we have principal bundles. Over Harishchandra pairs, we have principal bundles with connection, or just shortly we call them torsors. So if you have a smooth manifold and a Harishchandra pair, we can consider Harishchandra torsor over X, which is a principal G bundle, and L-valued flat connection form, which is an analog of a soldier form, but it's not G-valued, it's L-valued now. So, and let me now say what does flat and connection mean. So I'll explain this definition. I make it a definition, and not just a collection of words. So first, suppose that if you have a principal G bundle, then for every vector field, for every element of a Lie algebra, we can consider the vertical vector field on the total space of this bundle. And if you have a vector field on a manifold, you can take inner product with respect to this vector field, and you can take Lie derivative. So we have this collection of operations, and they satisfy the so-called Cartan relations, right? So commutator of the RAM differential and inner derivation is a Lie derivation, and the well-known Cartan operations from differential geometry. And we have two definitions. So let us call form a basic form if it vanishes under all of these Cartan operations. And basic forms are lifted from the base of our principal G bundle. And a connection form is something similar to a basic form, but no, it's an invariant, G-invariant form on a principal bundle, but it is not vertical. It does not vanish when we put a vertical vector field into it, but instead it acts by this rule, where iota, I remind, is embedding from small Lie algebra to big Lie algebra. So, in other words, on this map iota gives us a canonical L-valued differential form on a group G, and a connection form is an invariant form that restricts to each fiber as this canonical L-valued form on G. So this is what it means to be a connection form, and what it means to be flat. It's very simple. So it's a form in L-valued form on P. So it's an element of a tensor product of Lie algebra and the commutative differential graded algebra. If you have a tensor product of commutative differential graded algebra and the Lie algebra, we have a bracket. So it is, we have a bracket and we have a differential. So and the form is called flat if it satisfies Maurer-Cartan equation. So I'm being a little bit sloppy here because strictly speaking, I should be using topological tensor product here. And because if L is a profinite dimensional Lie algebra, then by this tensor product, I should mean the projective limit of A tensor these finite dimensional Lie algebras of which L is the projective limit of. But I'm being a little bit sloppy here, and I hope it will cause no harm. So yes, and here I'm being not so sloppy. So here another point of view which will be very useful for us is Kashut dual point of view on the connection forms. That suppose we have a profinite dimensional Lie algebra, and we can take the dual space, is a space of continuous homomorphisms from L to base field, and so but here when I think of continuous homomorphisms, I treat topology on the field of complex numbers as discrete topology. So I don't care about the fact that we have some norm on the space of complex numbers. The topology on L is just the Tikhonov topology of a projective field. And so we have a bracket, and we can dualize it to an operator from L dual to L dual tensor L dual. And here we have a completed tensor product, and here we have just a usual discrete tensor product of a discrete spaces. And we can state the operator data by Leibniz through to a derivation of the exterior algebra of L. And there is a very well-known proposition that delta squared is equal to 0 if and only if this Lie algebra was really a Lie algebra, so the Jacobi identity held.
So can you again explain the topology? I didn't quite understand. On
The
the right,
okay,
yeah,
the topology on L, or
this profile.
the topology on L is a topology of profinite of projective limit
Yeah,
of finite of discrete Lie algebras.
yeah, okay. And
So the topology on L dual is, one can say that this is the topology of pointwise convergence of homomorphisms, but it will be discrete. The point is it will be discrete.
what do you mean pointwise topology is discrete? Which one is this? It's either pointwise convergence or discrete, because for me discrete means that I mean there's no topology whatsoever.
Yes, I mean the topology of pointwise convergence of functionals is discrete. It sometimes happens. There are two topologies and they coincide.
Okay, so discrete and pointwise convergence, it means that discrete means that every point is open and closed in the same moment, right?
Yes.
Okay. Well, it can happen.
So there is a general fact that we have a category of discrete vector spaces, and we have the category of profinite dimensional vector spaces. Or if you want to think about them as topological linear spaces, that they're called linearly compact vector spaces. And these two categories are dual to each other. So the space of continuous homomorphisms from a profinite dimension of the dual space to a discrete vector space is profinite dimensional, and the dual space to a profinite dimensional vector space is discrete.
Mm-hmm. Okay, I just never heard about this, but I trust you. Never seen this. Is it probably some well-known focal effect, because I never heard about this? Okay.
No, I mean there is I'm not sure if I can give you a reference just right out of my hand, but it is, yes, it's. So yeah, and I mean, and another name for a profinite dimensional Lie algebra is just the space dual to a Lie algebra. So, but I don't want to talk about coalgebras, so I decided to talk about topological Lie algebras instead, because it feels more natural. Yes, and there is a fact about this topological tensor product, which I did not define it, but I mean, if I would define it, I would then it would be a theorem that this duality factor intertwines the tensor product of discrete vector spaces and completed tensor product of finite dimensional vector spaces. And this is actually a way to define it, if you already have this theorem about duality. So, okay, the gist of what I said is that if we have a finite dimensional Lie algebra, we have a differential graded commutative algebra, which is free as an algebra. It's called Chevalier-Limberg algebra. And these constructions, they determine each other, especially if L is not DG algebra, but just an algebra, then the augmentation here is unique. And so you can just reconstruct L from C of L as just this dual space to the space of elements of degree 1. And so we have a theorem of Quillen that from his work on rational homotopy theory, that if G is a profinite Lie algebra, then a Maurer-Cartan element in this completed tensor product is the same as a unital differential graded algebra homomorphism from Chevalier-Limberg algebra to A. So what is being done here? If you have an element of G tensor A, by adjointness, it's the same as a homomorphism from J dual to A, linear homomorphism. But a linear homomorphism we can extend to a homomorphism between algebras, a free algebra generated by G to A. A should be commutative algebra. And the theorem is that Maurer-Cartan condition here is the condition that this morphism commutes with differentials. So I have a proof for some reason here. I think reading this proof will provide nothing to no one, and this is something that I mean, there are just too many indexes, and this is something that should be treated as an exercise. So yes, if you allow me, I won't be. I'll just keep it. Yes, and
I think that the most non-trivial part of that proof was this topological property, in my opinion.
yes, maybe.
Okay.
Yes, anyway, and what will happen if L is not a Lie algebra but a part of Harish-Chandra pair, and we have an action of G on L, and so we have an action of G on the Chevalier-Limberg algebra of L. But this action is, I mean, it's sometimes called a smooth action or a homotopy trivial action. Again, we have operators, we have the full variety of Cartan operations. We have Lie derivatives and we have inner derivatives. So, and inner derivative work like that. If you have elements of treat elements of the symmetric algebra generated by L dual, by the skew-symmetric algebra generated by L dual, but skew-symmetric polynomial functions of L. This is just inner derivative, just plug-in of one of the arguments. And Lie derivative, it acts by the formula of Lie derivative. It is a commutator of differential, Chevalier-Limberg, and inner derivative. So yeah, and this operation satisfies the Cartan relations. And so why I'm telling you this is because we have a proposition that if you have a Harish-Chandra pair and we have a G-torsor, and if you have a form which is a flat Maurer-Cartan form here, it is a connection form, meaning it satisfies this condition if and only if the corresponding map intertwines the Cartan operators. Well, this is a calculation that one can perform. It's not hard. So, and from this fact, we can already just gather some truths as a result of having this definition. So we can define characteristic classes of Harish-Chandra torsors just by that. So let me put the definition in one place. Is that a Harish-Chandra torsor over X is a principal G bundle and a Cartan equivariant differential graded algebra map from the Chevalier-Hilbert algebra to algebra of forms on a total space of a bundle. And if you have such a map, a Cartan equivariant, we can restrict it to so-called, I mean, you can, not so-called, we can restrict it to the spaces of invariance. So we have a map from C of L to omega of P, but the space of Cartan equivariant forms on omega of P, this is the space of basic forms, they're all lifted from the base. So we have something that maps into forms on the base. And Cartan equivariant forms here, it is something that's called relative Lie algebra cohomology of L. So Lie algebra cohomology of L relative to G. And since we are working with profinite dimensional Lie algebras, here we should take what's called continuous cohomology.
Mhm. So
So
it's kind
yes, and this,
it's
yes,
very close to the Chern-Weil map, right? But it's not quite, because in Chern-Weil you have non-trivial curvature. And
yes,
here
yes, yes. Chern-Weil is actually, yeah, that's on my next couple of slides.
Sorry
So
for running ahead. Sorry.
no, I mean yes. So this is actually I don't know if this point of view to Chern-Weil construction is written somewhere, because but yes, the thing is that these are characteristic classes of flat bundles, but characteristic classes of general bundles are a particular case of the characteristic classes of flat bundles. So I'm now going to explain what I mean by that. So one example is the example of secondary characteristic classes. So if you have, for example, a flat real vector bundle, so for now, let everything be real. And a flat real vector bundle, it could be thought of as just jail bundle with flat jail structure, but we can take a Riemannian metric on this. Oh, sorry, we can take a Riemannian metric on this bundle, and we can take the SO bundle, the principal SO bundle of orthogonal frames of vector bundle, and it will still inherit the flat structure, but it won't be a flat connection SO form. It will still be a flat GL connection form. So we will have a Harish-Chandra pair, or Harish-Chandra torsor over the pair linear group, orthogonal group, linear Lie algebra, orthogonal group over X. So we have the corresponding characteristic morphisms from this relative Lie algebra cohomology to H of X. It is sometimes called Chern-Simons map. So there is probably you want to ask me how does this relate to the other definitions of Chern-Simons invariance, and for that I apologize. I probably cannot give you a comparison of this Chern-Simons invariance and any other Chern-Simons invariance in existence, but they coincide to some extent. Also, there is an equality sign. So I think this relatively algebraic cohomology is the same as the cohomology of Lagrangian Grassmannian of an appropriate dimension, which are given by the exterior algebra generators in degrees 3, 7, 11, and so on. This is step 4, but I kind of got. I mean, I became unsure of that just a minute before I started this talk, so I deleted it. But it should be the cohomology of Lagrangian Grassmannian.
Yeah, I mean, you taken GL equal to complex, right? GLC, everything else.
Yeah. Take first complexification, and then it's a unitary group factor by quotient by the
Yeah.
orthogonal. Yeah.
Okay. Yeah.
And the cohomology survives the complexification, even if it's real. Yeah. So, and another example is primary characteristic classes. So, to obtain the Chern-Weil theory from that, you must be willing to work with differential graded Harish-Chandra pairs, which, again, I won't define because it's not necessary, but you probably can define it by yourself. So only the Lie algebra needs to be derived. The group part will live as this. So the only differential graded Harish-Chandra pair we are going to use is this pair of G and cone over G, which is cone over G is the algebra that controls Cartan relations. It is G in degree 0 and G in degree -1, and the differential is the identity map. So if you have a connection form for a vector bundle, let's write down the curvature form for this connection, which is just something that is not equal to 0 if the connection form is not flat. And there is a proposition that we have this couple alpha and the curvature form with S just means the shift of the formal variable that shifts the grading. So this is the element of degree 1. So this whole thing is a flat cone-valued connection form on X. So it defines a G cone G torsor over X. So we have a characteristic map from the equivariant cohomology of this contractible Lie algebra, from the relative Lie cohomology of this contractible Lie algebra relative to G, and this relative cohomology is the space of invariant polynomials.
So I believe this is just the Weil algebra.
This is Weil algebra, yes. This is the Chevalier-Lenberg algebra of this differential graded Lie algebra is the Weil algebra. Yes, so this construction is not. But
That's why it's called Chern-Weil.
Wait. I mean, is it assumed that G is Pauli algebra or not?
Here it doesn't matter at all.
No,
Yeah,
I mean, is it true that it will be Lie algebra for infinite dimensional algebras too?
No, I mean this work for.
I think it's pure algebraic construction, no problem with the maps at all.
Yeah,
That's
this works for any Lie group with Lie algebra G.
No, I mean,
Yeah.
you told about Weil algebra, but usually Weil algebra is something very
It's
simple.
a different Weil algebra, sorry.
It's a different Weil algebra.
André
Yes.
Weil. It's not Hermann Weil.
Okay.
Yeah,
You're
it's
speaking about
something that
Hermann
is.
Weil. It's André
Okay.
Weil.
Okay.
No.
Then my misunderstanding disappears. Okay.
Yeah, it's the Chevalier-Lenberg algebra of this Condi algebra looks like this.
And as far as I remember, this is also a Harish-Chandra pair, right? As you told before.
I mean, this is a definition of a. This is an example of a differential graded Harish-Chandra pair.
Yeah. I just want to specify it again. Yeah.
Okay, so how do I get back from this drawing node? Okay. So this is a couple examples of how could we define the characteristic classes. The characteristic class construction, which is general and associates to every Harish-Chandra torsor some some invariants. And later in the process of this talk, we will define Rosansky-Witten invariance as the example of this. But yes, so another construction that we will need to use is the construction of reductions of Harish-Chandra pairs along the morphisms. So let us have a map of Harish-Chandra pairs. Again, what's a map of Harish-Chandra pairs? Harish-Chandra pair is a pair of group and algebra plus a map between two Lie algebras. And a map between Harish-Chandra pairs is a map between groups plus a map between algebras plus such that the square which you will be able to draw is commutes. And so if we have a torsor over this first algebra, we can just take a push forward on the level of torsors and then take a push forward on the level of connection forms. And you'll obtain a torsor over the second Lie algebra. So this is, for example, when you have a principal SON bundle, you embed the SON into JLN and you obtain a principal JL bundle. But this JL bundle, might remember that it came from SON bundle. So in any way, we will call the torsor that will obtain the push forward of our original torsor along this map. And we will say that the original torsor was a lifting or a reduction of the torsor pushed forward. And the difference is more between lifting and reduction is more or less in the approach. Because if this map is an embedding, it makes more sense to more sense to talk about reduction. And if this map is something like surjective, then it makes more sense to talk about liftings. So these two words could be used interchangeably. So an example, suppose that X is a symplectic manifold. And then the fibers of jet bundle natural admit symplectic structures, which again, I'm a little bit sloppy here. What is a symplectic structure on an algebra is a symplectic structure on the spectrum and on the formal spectrum. But it's not that important. So we can take the subset of the bundle of coordinate systems consisting of symplectic isomorphism between fibers of JX and standard symplectic disk. And this subset, it's a subsheaf of X chord, and it locally has a section. Why does it locally have a section? By Darboux theorem, because locally X is symplectomorphic to a usual symplectic disk with flat symplectic structure. And we have this group which acts on the sections transitively. So this subset is really a torsor of this group of formal symplectomorphisms. A normal the Grothendieck connection also preserves the symplectic structure. So we have a symplectic manifold because the vector field d over dx preserves the Darboux form. So if we have a symplectic manifold, we have a reduction of the torsor of formal coordinate systems from this big Harish-Chandra pair to a Harish-Chandra pair a little bit smaller. So this Harish-Chandra pair was associated with the formal power series algebra. And this is a Harish-Chandra pair of symplectic automorphism of formal power series algebra if we found a symplectic structure on it. And the claim is that this reduction fully determines the symplectic structure. So how could we reconstruct the symplectic form if we have this reduction? The answer is by means of the descent functor. So suppose we have a torsor, Harish-Chandra torsor over X. And we have a module over Harish-Chandra pair, which again, I the definition is more or less self-evident. But what I didn't define is what the Chevalier-Lindbergh algebra with coefficients in this module. So it's a statement that if we have a module over a Lie algebra, then we can extend the differential on the Chevalier-Lindbergh algebra to the differential of this free module over Chevalier-Lindbergh algebra. And this is how we define cohomology of a Lie algebra with coefficients in the module. So this is this construction. And if it was a module over a Harish-Chandra pair, then all this thing inherited an action of the Cartan operations. So this is what this Chevalier-Lindbergh module with coefficient V is.
Just sorry, just one small question. So
Yes,
alpha is a flat connection that is a map from Chevalier-Lindbergh to differential forms on P, right?
yes, which is equivalent with respect to Cartan operations.
Yeah, yeah, usual connection.
Yeah.
I mean, so just kind of glue V to omega P with the help of this.
Precisely. So on the level of group, it's just taking the associated vector bundle to a principal V bundle. We take the associated vector bundle on the level of
actually,
group.
you don't need the whole business with Chevalier and the complex. You just can restrict your attention just to the action of the V group, right? It is just
but
P plus V.
yes, precisely. But I also I want a flat connection.
Yeah, and flat connection. Yeah, it's known that if you have associated vector bundle and you have flat connection on principal bundle, then you automatically have flat connection on the vector bundle. It's kind of standard fact from a theory of connections, I believe.
Definitely, and this is how you obtain this.
Okay, yeah, precisely. Okay, thanks.
Especially because this is this is about not really connection, but the Harish-Chandra connection. Lie group is a little bit bigger.
Yeah, it's a little bit bigger. Yeah,
yes,
right.
Yes, but this is nothing exotic is going here. Yeah, this is very standard procedure. So we have a principal bundle with a connection. We have a module. We have a vector bundle with a connection. So, and yes, so yeah, and yeah, but what my point is that from this point of view, if by connection you mean just a homomorphism of differential graded algebras, then this descent procedure is just the push forward of modules. The general procedure, you have homomorphism of algebras, and if you have module over one, how do you obtain a module over the second one? By tensor product.
Yeah.
Yes, so this is a factor, and so yes, and for example, if you take the bundle of coordinate systems and you take descent of the formal power series algebra as a module over the group of the pair of automorphisms of itself, if you take descent of it, you will of course obtain the jet bundle with the Grothendieck flat connection again. You may take trivial module, and you will obtain a trivial bundle with trivial connections. So bundle of functions with connection being the Dirac operator. Or you can take some natural geometric objects on the formal disk. For example, you can take the module of a power vector fields on a formal disk. This is also a module over the pair of automorphisms of a formal disk. and you will obtain what's called the jets of the tangent bundle with the flat connection, with some analog of the Grothendieck flat connection with coefficients, and the space of flat sections of this bundle will be the tangent bundle. So in general, you can form jet construction with coefficients in different vector bundles, which I didn't talk about, but here is what happens.
So it looks like, so the last equality looks like the fact that the derivations of A come from the derivations of X. All derivations of, doesn't it? I mean, it looks very, I mean, there are no, it looks like the fact that there are no derivations of A unless you take some derivations. I mean, it's strange. If you manifold is actually just 1 point, what does it amount to?
I mean, if my manifold is actually 1 point, then the formal power series algebra with zero generators is just a base field, and I mean, not a lot of interesting things happen here. So
yeah, I mean, on the right hand side, there is no, because on the left you still have derivations, right?
I mean, you can treat this lower part as a definition of this right hand side. I did not define what a jet of the tangent bundle of X is.
Well, we all know what jets of bundles are. I mean,
yes. I mean, if you know that the statement is that this is the same thing.
Oh, so roughly speaking, derivations which can appear from local coordinates, they are all jets of certain vector fields on X, right? That's more or less what it claims. Derivations of jets which come from local coordinates, which correspond, not come from local coordinates, which actually accord with local coordinates, compatible with local coordinate systems, they all come from vector fields, more or less, right? Because jets of tangent bundle is more or less jets of vector fields, right? Jets of tangent bundle, they are jets of vector fields on X.
I mean, yes.
So on the left you have jets of so kind of sections of derivations, and the claim is that all derivations of A actually come from jets of vector fields if they are compatible with coordinate changes.
No, I mean,
I mean, the same question which Alexander Borisovich already asked, derivations are supposed to be continuous in some sense, right?
Of course, it was assumed at the beginning. Gosh.
Yeah, okay. Okay, sorry for being...
Yes, sorry if I did not answer your question, but yes, nevertheless, by descent of this module over the Harish-Chandra pair, we'll obtain a flat bundle such that the sheaf of its flat sections is a tangent sheaf. That is what I'm saying. Okay, and now suppose we have manifold with a reduction of the torsor of formal coordinate systems to this symplectic pair, and so over this symplectic pair we have a trivial module. We have a module of two forms on a formal disk, and moreover we have a map between them given by a symplectic form. So we can take the descent factor applied to this morphism, and we can define, and the image of one here will define a flat section of the jets of two forms. So it will define a globally defined 2 form. And it will be a symplectic form because it will be symplectic because symplecticity is a local property. Symplecticity is a property that can check in local coordinates and even in formal local coordinates. So we described a procedure how to come from symplectic structures to reduction of coordinate torsors, and here is a procedure how to go to the other direction. And these 2 procedures are inverse to each other. So symplectic structures are the same as reductions of coordinate systems torsor to this symplectic Harishchandra group. And this is more or less what is formal geometry is. So it is the study of various geometric structures on manifolds by means of studying the structures on jets, and the structures on jets are easy to describe as the reductions of the automorphism groups of jets. So, and the works of Fedosov and Nest Tsigan and of Kalezin Bezrukavnikov could be more or less treated as a realization that quantization, deformation quantization, is also a type of geometric structure. So you can apply this formal geometry method to the study of quantizations. So yes, let us talk about quantizations now. So let X omega be symplectic manifold. Again, it could be a complex manifold, could be a real manifold. It could even be an algebraic manifold because, but it should be smooth. And the deformation quantization on X is a sheaf of associative algebras over formal power series ring, which is locally isomorphic as a sheaf of modules or formal power series modules to O of H. So it's a flatness condition. And such that modulo H, this sheaf is isomorphic to O as a sheaf of algebras. I think there is a mistake. The word locally shouldn't be here. Modulo H, it is isomorphic to the sheaf of algebras, to the sheaf of functions as a sheaf of algebras. And we need the condition of compatibility with a symplectic structure. And this compatibility is that it is given by a symplectic structure in the first order in H. So an example, which probably everyone knows, that if we have just a flat space with a standard Darboux symplectic form, then the Weyl algebra is a deformation quantization. So I say here suitably completed. By suitably, if I treat X is just a algebraic manifold, that I don't need to complete anything. If I treat X as a holomorphic manifold, I need to complete it in the way that I allow like convergent series in Z and omega, like series with infinite radius of convergence. And if I treat this as a real manifold, I need to complete it even further. So that's why to not deal with questions of completion, one usually defines it by means of the Moyle-Weyl formula, but it's not that important for me. So because I'm going to use the formal version of the Weyl algebra anyways. So there are a lot of variants of this Weyl algebra depending on what series are you allowing yourself to consider. You can take formal series, convergent series, just polynomials, or what.
You mean
Yes.
the convergence with respect to H, right? Like in Fedosov quantization, something like that.
No, just with respect to Z. Just what are you allowing? Are you allowing only polynomials in Z, or are you allowing like formal power series in Z?
Yes, I mean, but using formal power series, you need to say something about the well-definedness of that algebra.
Yeah, I mean, for informal power series, I don't need to say a lot of things. If I want to use convergence series, yeah, I need to say something. I avoid this question.
There are some subtle things. So, well, if you add this commuting formal variable h into the game, then okay. Well, we had before many talks about these completions by George. He explained us this Fedosov approach, and then all the definitions were given. That my question is just you used the same definition like in Fedosov work, right? Right?
Yes, definitely.
Okay.
I mean, so on the next page and further on, I'm going to use only the formal version of all this, like in philosophy, yes. So, and here I'm being vague when saying that suitably completed. I'm not saying what suitably is, because for different purposes, you need different completions, and some of them are complicated. But anyway, yes, and so the question is why it is flat as a C of H module. The answer is by Poincare-Bergov field theorem, more or less. So again, one need to talk about quantization of formal spaces and schemes, but I mean, most importantly, about quantizations of a formal disk, formal symplectic disk. And the formal Weyl algebra is a quantization of a formal symplectic disk. And moreover, there is a following quantum formal version of the Darboux theorem that all quantizations of a symplectic formal disk are isomorphic to Weyl algebra. And moreover, yes.
So how is this proved?
It's a computation. I mean, a computation is Cauchy cohomology. Just you can classify all non-commutative deformations of
Just
power series algebra and just say which of those are quantizations.
Yeah, I understand now. Yeah.
You need a bit of formal deformation theory to do that. Yes, and to a formal Weyl algebra, there is associated another Harish-Chandra pair, which will be the main object of our further study. So the group of automorphism of Weyl algebra is a profound dimensional Lie group, because it's also, and this is a pluripotent extension of the symplectic group, because its Lie algebra is the Lie algebra of derivations of the Weyl algebra that preserves the maximal ideal in it. It embeds into the bigger Lie algebra. So you have two Harish-Chandra pairs. And by factoring out the formal variable, you obtain two surjective morphisms between quantum Harish-Chandra pairs and symplectic Harish-Chandra pairs. And so we will need for a quantized manifold, for a manifold with a quantization, we will need to define a version of a jet bundle. And for that, I think it's not very convenient to work with local coordinates, and it's easier to take the approach that comes from algebraic geometry. But yes, so let us give another definition of the jet bundle. So in a non-coordinate way, we could describe a jet bundle of X as the following sheaf. We have a product of X by X. We have the ideal of the diagonal. and we can take the completion along the diagonal, which is a formal, and we'll obtain the formal neighborhood of the diagonal on x by x, and we take push forward to one of the coordinates, and yeah, this is a jet bundle. And yes, in algebraic geometry, the sheaf of functions on the product is just the tensor product of two sheaves that come from one factor and the other factor. Yes, if you have a polynomial function of two variables, it is a finite linear combinations of products of polynomial functions of each variable. But it's not true if you take a holomorphic function of two variables. You need to allow yourself to make infinite linear combinations. So that's because here there is a little hat, and the little hat symbolizes that to obtain a sheaf of functions of two sets of variables on a product of two manifolds, you need to take this exterior tensor product of sheaves that come from each factor, and you need to complete it, with respect to the usual form that you have in holomorphic functions. Is a form that supremum on all compacts, is uniform norm of all compacts. If you complete this algebraic tensor product with respect to this collection of norms, you will obtain the space of holomorphic functions of two variables.
Is it the same as when you obtain if you want? Is it the same tensor product, completing tensor product, which you need to use if you want to obtain the same result for smooth functions? Or for
no, for smooth functions you need to
there are different tensor products.
You need to take a different collection of norms, because in complex analysis you have a theorem that if you are on a compact, then if you have a uniformly convergent sequence of holomorphic functions, its limit is holomorphic. Yeah, by Cauchy theorem. But this is not true for smooth functions. For smooth functions, you need a collection of norms that controls also all the derivatives.
And for continuous functions, you just need something even simpler than the first one, right?
Well, for continuous functions, I think uniform norm is enough.
Uniform norm, okay. Yeah. Can smooth ask for some additional measures.
Yeah. So why I am explaining this so much? Because we need to define a quantum jet bundle. We need to take the analogous. We need to perform the analogous construction, but in a different way. So we take the algebra of usual functions on one factor, and we take the quantized algebra of functions on the other factor, and we take their product. Again, completed. And we complete it with respect to ideal generated by the functions on the diagonal, and by H, in other words. And
sorry, if we try to translate this into the language of philosophy, I think it's just the philosoph's completion of the sections of Weil bundle, right? Of Weil algebra bundle. He also introduces this completion, right?
Yes, I mean, as a result, you will obtain Weil algebra bundle. Yes.
And completed by philosophy.
Completed, of course.
Okay.
Yes, and how to define the Grothendieck flat connection in this setting. So here, the Grothendieck connection is just the de Rham differential along the first tensor factor. And here is the same. You have a flat connection. This is the de Rham differential along the first tensor factor. And the space of flat sections here are the space of regular functions. The space of flat sections here is just the sheaf of flat sections here is just our quantization sheaf. So if you have a manifold endowed with a deformation quantization, we constructed a sheaf with fibers being algebras of power series of several variables and of h, such that its reduction modulo h is just the jet sheaves. And what it is the same as the reduction between is the reduction of x coord to this quantum Harry-Chandra pair, and actually it's the reduction of x dark to this quantum Harry-Chandra pair. So in that sense, quantization is also a geometric structure. So, and how to obtain from a reduction of x dark to quantum Harry-Chandra pair, how to obtain a quantization? Well, you take descent of the Y algebra. This will be a quantization. This will be a sheaf of algebras which will satisfy all the required properties. And so there is a little caveat to this because there is a different quantizations. They might be isomorphic via an isomorphism that is identical modulo H, but not identical in general. And different reductions could also be equivalent in that sense via a gauge transformation that is identical modulo H, but in general maybe not identical. So the statement is that these equivalence relations, they correspond to each other. So gauge equivalent reductions of coordinate system torsors lead to isomorphic deformation quantizations. So yes, and now the problem of classifying deformation quantization is reduced to the problem of classifying lifting of torsors from one Harry-Chandra pair to another, but we can simplify which should be simpler, but we can simplify the problem even further by getting rid of the group part of Harry-Chandra pairs, well, mostly completely. So we have a pair of full automorphisms of the formal power series algebra, and we have a sub-pair of linear automorphisms and all the derivations. And the reduction of the torsor of coordinate system, it amounts to the choice of a global isomorphism between the jet bundle and the completed symmetric algebra of the bundle of one forms. And you can see that it is always possible to do in the smooth category, but because in the smooth category every short exact sequence of vector bundle splits, but in the holomorphic category it is not always possible. But it is possible to do this smoothly for holomorphic manifold and just keep track of the holomorphic structure that was there before to obtain some different holomorphic structure. So I mean, this is more or less what is being done in the Kapranov article on Rozansky-Witten invariance. So so yes, and before I'm starting to talk about this, please tell me how much time do I have, because I'm talking for an hour and 20 minutes already.
Yeah. So, well, I think we can actually count on another 20 minutes, but, well, wouldn't recommend to exceed this limit by too much.
Yes, no,
So-
I think 20 minutes, yes, I'll try to be first quick and second understandable.
Okay.
So yes, so yeah, our problem is to find some non-standard holomorphic structure operator on the sheaf of on the completed symmetric algebra on the sheaf of 1-0 forms. So and this is well,
It was
this is,
can you please repeat the reduction on what map? Just show me the previous slide.
yes. So the reduction, the reduction of X coord along this map, the reduction of the jet bundle from to a linear bundle.
So you have a jet bundle which is associated with automorphism and derived function.
Yeah, and we want to reduce its structure group to just a linear group instead of the group of formal coordinate changes.
So it's actually like going from the complete X coord to just a linear part of X coord, right?
Yes.
The frame bundle on which lies inside. Okay. Yeah, just this. Yeah, you can go on. Sorry.
I mean, we can always come to frame bundle, but the point is to find a way to obtain the full jet bundle from the frame bundle using only linear changes of coordinates. So okay, and this is, I mean, this is the procedure that in works of Fedosov and Nestigan is done by proving that the abstractions to solving the problem vanish, so you can choose some answer. But here, this can provide actually like not very explicit formula, but something nevertheless. So I mean, probably not much sense trying to explain what this formula is, but anyway, so this recursion, it defines an automorphism of this bundle, which is actually a flat connection on it that squares to 0. And the operators that are terms of this connection, they are expressed via the curvature of some torsion-free connection. So we start from a torsion-free connection and we take operators depending on it, mostly curvature and its covariant derivatives.
Well, as far as I can understand, I have the following idea.
Yes.
You have non-flat bundle, of course, right?
Yes.
But you have a torsion-free connection, but then you add to the usual connection terms which take values in the derivations of the formal power series bundle.
Yes.
And that makes it impossible to make it flat after all, right? Just by adding.
Yes.
And this is more or less, and the formula we have here, it looks like the homology perturbation lemma a little bit.
It could be obtained by homology perturbation, yes.
Because K looks like the homotopy.
Yes, it is precisely the homotopy. It is the homotopy operator for this A0. Yes, yes.
Thanks.
Yes. So okay, and the theorem that allows the simplification is that we have the torsor of trivializations of this bundle with this holomorphic bundle with the connection that we just constructed, and we can take push forward of these to the full coordinate changes Harish-Chandra pair, and the theorem is that these torsors that this bundle that we just constructed is actually the jet bundle. And the proof of this is some universal property of the jet bundle or the formal coordinate systems that I probably don't have time to explain. But the proof is some universal property of the jet bundle. And again, we can do the same for if you have a holomorphic symplectic manifold, we can do the same reduction by differential geometric methods and homotopical perturbation, not for coordinate bundle, but also for the torsor of Darboux formal coordinate systems, and if you have quantization, that for quantum Harish-Chandra pair also. So if you look at this commutative diagram and notice that everything here commutes, and the thing here has a certain universal property, then you can convince yourself that the question of lifting torsors from here to here is the same as lifting torsors from here to here. And this is much simpler because the group part is the same. And you only concern yourself with the connections. So yes, and here I'm saying that the map from derivations of Weyl algebra to the formal Hamiltonians, Lie algebra, is a deformation. So what do I mean by that? I mean by that the derivations of Weyl algebra, it's algebra over formal power series, such that it is free as a module over C of H, and quotient by H is a Hamiltonian algebra. So the non-trivial property here is freeness, and this again that follows from the Poincaré-Birkhoff theory, and fact that almost every derivation of Weyl algebra is inner. So we have Weyl algebra. To each element of Weyl algebra, we can construct a derivation of Weyl algebra by just a commutator. And if you just fix it a little bit, just add 1 over H to here, this will be surjective map. Use the kernel, just constants. And from the flatness here and the flatness here, we'll obtain the flatness here. Yes, and as we said before, Lie algebra structures are the same as derivations z squares to 0. So we can describe deformations of Lie algebras as just Maurer-Cartan elements in the Lie algebra of derivations of Chevalier-Lenberg algebra. So, and here we have a suitable definition of a deformation of a Harish-Chandra pair. It's just a map of Harish-Chandra pairs that such that on the group part it is trivial, and on the Lie algebra part it is a deformation. And we can give the same definition of a deformation of connections. So if you have a J torsor of X and you have deformation of a Harish-Chandra pair, you have a Maurer-Cartan element, then we can describe a graded Lie algebra, which is not strictly speaking differential graded Lie algebra, but it will be differential graded Lie algebra with a curvature, such that the Maurer-Cartan elements here will will be liftings of Maurer-Cartan's element from here to here, and it is just the algebra with this is more or less for a flat bundle. This is the Lie algebra. This is the RAM complex of the adjoint flat bundle, which is flat, but then we deform it, and the curvature starts to appear. So because iota of alpha is not a Maurer-Cartan element anymore, we will have some. This won't be 0, but this will be divisible by h. But okay, this is still this data of 3 iterations. It will be a curved differential graded Lie algebra, and just curved differential graded Lie algebra is a Lie algebra with a differential and curvature operator such that d square is not equal to 0, but d square is given by the commutation with the curvature operator. But you can talk about Maurer-Cartan equations, curved Lie algebras, and you can talk about gauge equivalence between Maurer-Cartan solutions. And moreover, if you have a description of some problem, these Maurer-Cartan sets and equivalence sets of Maurer-Cartan equivalence classes of curved Lie algebras, they behave rather well with respect to homomorphism of curved Lie algebras. So if we require this weakly curve, if we require that curvature element will be divisible by h, then if you have a curved Lie algebra, then its associated graded modulo h is a complex, then d squared will be equal to 0. We can take cohomology, and we can say when the map between curved Lie algebras is a filtered quasi-isomorphism. It's filtered with respect to this h-adic filtration. And theorem is that this set of equivalence classes of Maurer-Cartan elements is a filtered quasi-isomorphism invariance. Moreover, it is then it is very, very easy to describe this Maurer-Cartan set for an infinity algebra curve that's filtered quasi-isomorphism to an abelian Lie algebra with no curvature. It's just the first cohomology. And we have a theorem that is might be considered as a deformation theoretical version of the implicit function theorem, is that if you have a map of differential of curved algebras preserving curvatures, such that this is homotopy abelian, and on the cohomology level, after taking associated gradient, this is an injection, then this is homotopy abelian algebra as well. So yes, this is not the most general form of this statement, but this is what we'll need now. And so a slightly more general form of this statement is a version of this statement that allows for L-infinity maps, and L-infinity map between two, say, curved Lie algebras is a map that does not preserve bracket explicitly, but it preserves bracket up to homotopy, and then this homotopy must satisfy some properties. So here are the definition. Here is defining equations of an L-infinity morphism with only 2 parts. So with F3 and next thing I0.
There is no relation between HL and HM and F2. I cannot see any. I mean, the only relation which involves the curvatures is F1 of HL is equal to HM.
Yes, I think if it's an L-infinity map, just an honest L-infinity map which has no curvature element, then only thing that I require is that the curvature maps to curvature. You can relax this. You can relax this, but this is enough. And this is what will happen in the next slide.
So why do you need the curved Lie algebras? Can you again? Because
I mean, because I'm studying the quantizations, And we just showed that the quantizations are solutions of Maurer-Cartan elements in some curved Lie algebra. Because I cannot get rid of the curvature.
Because H is the curvature, right? H.
Yeah, quantizations might not exist for once.
Mhm.
And if you have an uncurved Lie algebra, then this Maurer-Cartan set is always pointed by 0. But if you have a curved Lie algebra, then this Maurer-Cartan set is unpointed. You don't have a distinguished Maurer-Cartan element.
Can you again show me this curved part? I didn't quite understand it. So this is
This?
geotorso.
I mean, no, this is just not a complicated thing. That you have alpha was a Maurer-Cartan element in L, but then you add some higher terms to L, which is just deformation, and it stops being a Maurer-Cartan element. The curvature appears. So there is a slight mistake. This should be iota A, where iota
Okay.
is the splitting.
And this gives you H, and actually the question is if you can complete with this further by adding
Yes,
further correction
Yes.
terms to all this.
So, and the period map, which is a main point of study in the works of Tsigan and Kalinin Bezrukavnikov, is actually an L-infinity map that comes from these two central extensions that exist here. So let us describe this curved algebra such that controls the quantization problems. So it's an algebra of differential forms times Hamiltonian vector fields, and Hamiltonian vector fields are just functions quotient by constants, times H. With a differential given by this Kapranov construction, that inductive construction that I showed a little while ago. And yes, so this part is flat, and this, when I add the H parameter, it stops being flat because the bracket changes here. And the statement is that if you have an L-infinity map, which we construct in that way from the cocycle defining the central extension, we will obtain an L-infinity map. So all these defining equations of L-infinity map will be true. And how to prove from that theorem of Nest and Tsigan, we should show that this first map, if we calculate the cohomology of everything that we have, modulo H, we will identify this map with the standard embedding of the cohomology of first cohomology of shift Hamiltonian vector fields to the second Ram cohomology. And if it is an embedding, then from the theorem, from the implicit function theorem, we have classification of quantizations. Because this is a homotopy abelian Lie algebra, and the quantizations are controlled by cohomology. So this is theorem of Nest and Tsigan. And yeah, so let me show the last slide. So what we can do with this is, I mean, one calculation that we can obtain is that we can relate the quantization problem with so-called Rosansky-Witten invariants. What are Rosansky-Witten invariants? Rosansky-Witten invariants are Gelfand-Fuchs invariants associated to this linear part of Darboux coordinate torsor. So so we have a Rosansky-Witten map from this Lie algebra to the cohomology of the Dalbo complex of the jet bundle together with the flat convection. So I mean the cohomology of thing is the cohomology of structure shift, because this thing resolves the structure shift. And so there is a canonical element, Mayal-Weil element, sorry, defining the deformation, Weil deformation. And the curvature element is equal to the Razansky-Witten invariant of the Mayal-Weil element. And if you know how to describe Razansky-Witten invariance in terms of graphs, how to describe elements of this complex in terms of graphs, then in terms of graphs, this Razansky-Witten invariant of Mayal-Weil element is the sum of theta graphs. So I think this is all I wanted to say. Thank you very much.
Okay, thank you. It was quite instructive, and it's a pity you had to hurry so much in the end, because the most interesting, in my opinion, part of your talk was the last
Yeah, I understand.
well, 10 slides or about so.
Mhm.
And I just wonder if there are any questions, because I have lots of questions, but if I were allowed to ask them, we would continue for another hour. So probably withhold my questions. I just send you questions in email, okay?
Sure. I would be glad
Yeah,
to.
so probably somebody in the audience has some questions. Yeah, please be brave and ask the questions. I have another about some, have a few minutes to ask the questions. Okay, yeah.
Difficult
Yeah,
to ask. Well, all questions were at the beginning, but I think, I mean, for probably we should take 2 times instead of 1. It's but too difficult to understand things at the end. Okay.
Okay, so let us thank the speaker. It was
Yeah.
really very interesting talk. Just it's a pity we didn't have enough time to.
I mean, in principle, sometime
Maybe
again,
we can
I
repeat.
might just give a continuation of this talk. So
Yeah, if they will be happy. Okay, I'll send you a message when you. Yeah, just let me know when
Maybe
you.
there are some questions from other participants. I don't know.
Are
Some
there?
of them
Let's see.
just
Maybe
joined.
I ask one question.
Yeah, sure.
One of applications of deformation quantization is to index theory by Nest and Tsigan, and also by Fedosov.
yes.
Do you expect a connection to index theory of what you talked about today?
I mean, so yes, but not much. So this period map is I mean, this period map is part of the formulation of the index formula due to Fedosov, Nest, and Tsigan, because they have some index formula which involves the characteristic class, this characteristic class, and characteristic class of quantization. That is a period map. These methods, these infinity methods, are potentially allow a more effective procedure to calculating this period map.
Oh. By the way, then I have a question, a very small question.
Yes.
Really, I would like to ask now. One of the major properties of Nest and Tsigan theory was that they actually showed that Fedosov's classes can be reduced to something smaller when you work with holomorphic case. And then there are these tau n maps from certain part of cohomology, which restores the missing part of the cohomology. Where is this in your construction? Where are these tau classes here?
Here they are.
So these are tau.
I
Because
mean,
what
so
is theta and V? Because in their context, they had certain amount of
I mean,
two forms.
beta and V, they're just dummy variables. So just
Sorry?
these are just dummy variables.
What variables?
Dummy.
Да. Скажите еще раз по-русски.
Ну, dummy переменные, глупые. Ну, в смысле, они ничего не значат.
Какие?
Dummy.
Dummy. Oh, sorry, dummy.
Да.
I didn't understand. Okay. Okay, yeah, I understood now. I didn't
Yeah,
expect
so-
this to appear
Yeah,
here.
this is a connection form. So yeah, how to obtain tau classes?
Yeah.
One needs to take homotopy transfer and to transfer these to this, and
Okay.
write down a quasi-isomorphism between this and this, and then quantization will be element in here. The period map will go from here to here, and the image of this will be, I mean, not from this, but this series in H.
Yeah. Yeah.
Yeah, and the image of the quantization will be some series in H, and the coefficients of this series are tau classes.
I mean, tau classes, they are in H20, 002 part, right? Of the de Rham cohomology in Neston-Segan context. Tau classes.
H20 plus H11, yes.
Yeah, so 02, right? Sorry. Tau classes are in H202, right? And on the left, so there is a map from H20 plus H11 to H02, and that's what I call tau. So where are they here? Because on the right you have H20 plus H11 plus H02.
Yes.
And on the left, what do you have on the left?
On the left, I have H11 plus H20.
Oh, that's because omega de Rham is holomorphic, right?
Yes.
Just what's the difference?
Yes,
Oh,
and tau
so
classes.
you take greater than one. Yeah, that's
Yeah,
this
because it's not the de Rham cohomology. It's de Rham cohomology. It's a cohomology.
truncated de Rham.
This complex of shift is quasi-isomorphic to a shift of Hamiltonian vector fields.
Yeah, I see. And
Or
it's
to close one,
truncated,
yes.
it's truncated de Rham. It gives you H11 and H20. It doesn't give you
Yes.
H02.
And I think the restriction of this period map to H02 are tau classes, but I need to double check.
On the right-hand side, restriction to
Yes.
0 to. Okay,
Yes.
yeah, that's what I asked. Yeah, thank you.
Thank
Now
you.
I'm quite satisfied. And I'll send you lots of questions in email, but not today. Okay.
Yeah, sure.
I mean, it's pretty late in China already. Okay.
Yes.
So thank you very much for your talk. It was very interesting. And in a week, next week, we will reconvene. I'll send the information to everyone online by email on weekend. Thank you for your attention. And thank you for your talk.
Thank you.
Thank you.
Yeah, we can just leave the conference. Everyone can just press the
Goodbye.
button to leave.
Спасибо еще раз.
Спасибо вам.
До свидания.